Hello, welcome back. Good afternoon, everyone. I am Michael Buning. I am the Director of Performing Arts and Culture here at Asia Society Texas. And on behalf of Asia Society Texas and Teamwork Arts and Imprint, I want to welcome you to our next session we're very excited about. It is The Big Bang of Numbers with Manil Suri in conversation with Maya Kanwal. And this session is being presented by Bella Jane. In Mathematician and novelist Manil Suri's latest book, The Big Bang of Numbers, How to Build a Universe Using Only Math, he embarks on a mathematical origin story spanning the universe, an inspired and insightful journey through the fundamental mathematical concepts that form the cornerstones of our existence. Suri's visionary work takes us on a riveting journey to infinity and beyond. And he will be talking about this work today with Maya Kanwal. Manil Suri is the author of The Death of Vishnu, The Age of Shiva, and The City of Devi. He is a distinguished mathematics professor at the University of Maryland, Baltimore County, and has written frequently for the New York Times. Maya Kanwal is a Pakistani-American writer from Houston and fiction editor at the Gulf Coast Journal. Her work appears in Witness Magazine, Meridian, Quarterly West, and other journals. She holds an Master's in Mathematics and is an Imprint C. Glenn Camber Fellow at the University of Houston Creative Writing Program. We will have a Q&A following the initial conversation, as we have done in past sessions. And there are books for sale. The book, The Big Bang of Numbers, is available for sale outside at the Brazos Books table, and there will be a signing after this session. So let's get started, and we are very happy to welcome to the stage today Manil Suri and Maya Kanwal.
Hi, everyone. How are you? So this was, it's taken me so long to write this book that I've been entertaining myself by making little PowerPoint videos, and that's one of them. So this is, of course, Thus Spake Zarathustra, which, if you remember, it's from 2001: A Space Odyssey. I call this 2000X, an algebra odyssey. But algebra is still a ways ahead. This is actually, my book starts with numbers, like what are numbers, where do they come from, how do we make them? And I'll just, before we start the conversation, I just want to tell you a little bit about how all this came about. Back in, I think, 1977, I was a physics major in the University of Bombay, now Mumbai. And we had a professor, his name was Huzur Bazar. He was teaching mathematics, and he told us about this famous quote by Kronecker, a mathematician, who said that God gave us the numbers, and the rest all is the work of man. That is, that human beings developed everything from the numbers. And then he said, well, I'm going to prove Kronecker wrong, and I'm going to show how you can even obtain the numbers that man and human beings can construct numbers as well, out of nothing. And he proceeded to show us this, and it's one of the basic things one learns in mathematics as a undergraduate. And that experience was so transforming, it really felt to me like numbers were just coming out of the screen, out of Professor Huzur Bazar, and the walls were dissolving, and the whole cosmos was just numbers. And it was almost, it was probably the closest I've had to a religious experience. I soon switched from, I was a physics major, I switched to mathematics, and then started doing my studies in that, and then of course, much later discovered that I was also a writer, wrote my novels and all that. But in the back of my mind, there was always this question, can I share this love of mathematics, this experience that I had with people who haven't been exposed to mathematics, but would like to know more about it. And it struck me that, when you talk about the origins of the universe, the origins of everything, you think about religion, like Brahma blowing out the whole universe in a single breath, or Genesis, where God creates everything in 7 days. Or you think about physics, where there's supposed to be a singularity and mass and energy are concentrated in like a single point, and then something happens, and then you get the whole universe starting from that. And I felt that this construction of numbers is close to cosmic creation, but in a very different way, that you can actually start with just nothing in the form of something called the empty set, and then you can build the numbers, and from numbers, you can build geometry, and carrying on like that, you can actually create a lot of things. You can create physics, you can create basically the whole universe. At least that was the attempt that I said, okay, let's see how far I can go. Huzur Bazar taught us how to do the numbers. How far can I go in this? And eventually, the book that came out of this was divided into 7 days of creation, but now you're not creating like God did in the Bible, but you're creating arithmetic first, and then you're saying, okay, you the audience, you the reader, is in the position of the creator, and you're saying, what do I need next? And it turns out you need geometry next. Well, what do you need after that? You need algebra to communicate these ideas, and so on. So it's a process of discovery. It's a process of experimentation. It's a process of playfulness, which is one of the things that mathematics has that is so attractive to me and to many others. So I'm putting you in this driver's seat in this book and helping you see how each step of mathematics can create the universe. And whether we make it or not, that's a different story, but that's the idea. And I'm also empowering you to see with very simple mathematics what you can do, putting you in the driver's seat so that you can experience this playfulness, this progression of ideas yourself. So that's what the book is about in a nutshell, and now I'll come to the proper part of this conversation. So great to have, somehow the JLF, hats off to them. They found another mathematician turned writer. That's, it has to be a cosmic coincidence. So.
No, it's brilliant. I feel like we both had the same launch into mathematics. That's when it's the same class I had up in Rochester that just I couldn't go back. But let's address the elephant in the room, Manil.
Okay.
How much of a math brain does one really need to be able to follow your book?
Okay, so that's a great question. And so in the book itself, I have used, this algebra comes on, I don't know, page 120 and so on. And the only things I use are things that you would have learned in high school, like quadratics. Basically, that's it. No calculus or anything like that. So the math itself, if you leaf through the book, you'll see there are almost no formulas. There's a kind of saying that each time you put a formula in, you lose half your audience. So I've been very careful about that. What you do need is two things. The first thing, the most important, is you do need some sort of interest. What I say in the beginning of the book is, I've never had a interest in cricket. I know that's awful for someone from India, but I have to live with it. But if you have no interest in mathematics, stay away from this book. But there's a lot of people that I meet that always tell me, I wish I knew more about math. I wish, I was good at it in grade school or high school or whatever. Then I went off and became a writer or painter, and I've never been able to reconnect with it. I think that kind of interest would really help you read the book. And the second thing I would say that you need is you need a little bit of patience, because even though there's no real math in it, there are a lot of ideas in this book. So you have to be able to say, okay, I've read a chapter, and what are the ideas in this? And let me kind of, not read it like a novel. So you might have to spend a little more time on it, like good nonfiction, I think.
Absolutely. I think all of those ideas, it was just when we were in Roberto and Rich's talk earlier, I felt like we might almost be doing a replication of those concepts in just this different context. So yeah. Well, so we've talked about how it can take 7 whole days to build the universe. Seems like mathematicians can do it in about 300 pages. But maybe we can practice a tiny bit. And you mentioned nothingness, starting from nothing. The void has always been pondered by priests and philosophers and poets. So let's start with the void.
Okay.
Little emptiness in my palm over here. Could you take us to the number 2?
So that's a great question. And the first question that arises is, what do you mean by nothing? And I was just doing an interview with someone who has a series on the web. His name is Richard Lawrence Kuhn. And he has actually written a paper where he talks about the 9 levels of nothing. The first level is just where you take everything away. But that really leaves emptiness rather than nothingness. You still think there's some sort of container. And then you start removing mass and energy and physics laws and so on. So there's different types of nothingness. And it gets pretty complicated. Physicists try to define what this means. As you said, in India, I think Hinduism has often, and Buddhism has often spent a lot of time contemplating what it means to be the void. And some scholars have said that's how they actually invented zero. They gave a name to that void, and that was zero. Interestingly enough, mathematicians do something very similar. Their idea of a void is something called the empty set. Now, I should say that whether you're a physicist or looking at it from a religious point of view, there's always something you start with. This is a kind of magic trick. Whether you're looking at what religion says about origins or what physics says, there's always, well, what came before that? Mathematicians are very cut and dry. We tell you exactly what we start with. And we start with not exactly nothing, but something called the empty set, which is a mathematical idealization of nothing. Once you have the empty set, you equate that to 0. And notice now you suddenly, once you start putting words to this, you suddenly have something. You have the number 0. And that is something that you can now, again, looking at it as a set, you can say, hey, I can now put this 0 inside another set, and I can now get the number 1. Now you have 2 objects, 0 and 1, so you call that sense of being dual, having this double thing as 2, and then you keep defining successors in this way. And before you know it, you've got 3 and 4 and 5 and 6. And if you go to my website, manilsuri.com, you will actually be able to see a video that goes through this process and tells you how that's done. And then, interestingly, that's what I call the Big Bang of numbers, where this process can be regenerated again and again, and suddenly you have the whole explosion of all the numbers, all the counting numbers.
You've got infinity.
You've got infinity, so to
cheated.
speak.
You got us not just to 2, but to infinity.
Yes, exactly. So how's that for 2 minutes worth of work, right?
You
Already
guys are
at
amazing,
infinity.
and everybody got this.
Yeah, right.
No, so what's interesting too is in this conceptually now you've built an ordering. Obviously, you can say what's larger and what's smaller as far as how many sets or how many containers you've built up.
And I'll just point out that that's something we don't think about, but in language we say larger, smaller. Well, all of this comes from math. If you didn't have this sense of ordering of numbers, you wouldn't be able to say large and small. What would that mean?
Exactly. And then with this ordering also, we've got addition and multiplication conceptually comes in very easily in the same construction. And all we've done is described what this construction is.
And I will say something else. Being a novelist, I've been working on this book for a long time. And one of the several versions, I would say, one of the versions was a novel. And so what I decided was the numbers would be alive, that they would be the characters of my novel. My editor was not too thrilled with that. So what I did was, in this book, I still retain that conceit, and the numbers do play a role in actually playing games. And so, I understand addition and multiplication and so on, like games that numbers are playing. And that, again, brings out this playful nature of mathematics.
Exactly. I think what's interesting, what this exactly leads us to is, how much math likes trouble. So, we were comfortable with the addition and the multiplication, but suddenly addition also implies subtraction. And if you start messing around with subtraction, suddenly we've only built 0, 1, 2, the natural numbers. We hit this wall. And this is where we would end up with the negative numbers, right? Then you've got to construct those. And I guess my question is, or one of my observations throughout this book is, how much creativity there is in math when trouble happens. You hit this point and suddenly you have to invent a whole new concept to satisfy. So could you talk more about that?
Yeah, so this is one of the nice things about mathematicians look for trouble, like you said. We are always talking to engineers or medicine people or whatever, asking, well, did you run into a problem with something, and is it something that we can attack using mathematics? And so this is kind of the simplest, kind of the prototypical example where if you think back historical human beings probably developed the counting numbers. They used things like notches on a bone, and that's how they actually figured out 1, 2, 3, 4. Many cultures did not have numbers, did not have words for higher numbers because they might have only dealt with up to 4 or up to 5. So how did they get to the negative numbers? Well, as Taiba just said, what happens is if you start looking at the inverse of addition, 1 plus 2 is 3, so can these numbers who are playing these games kind of subtract 2 from 3 and get back 1? Well, yes, they can. Can they say 2 plus 4 is 6, and therefore 6 minus 4 is 2? Yeah, they can go back and forth. They can do this nice little dance. But let's say that you say something like 2 plus 4 is 6, and then you want to subtract 6 from 4. 4 minus 6 is what? Well, what is it? You don't have a number. You don't have anything there. You've only developed the counting numbers. So what you're forced to do then is come up with new numbers. So this is, a way to give birth to entire new families of numbers. Similarly, when you do division as a complement or inverse of multiplication, 3 divided by 2, what is that? I mean, 6 divided by 2 is fine, that's 3, but 3 divided by 2, well, again, you need more numbers. So mathematicians have to invent things. And throughout mathematical history, there have been inventions that have carried this ideas forward. I should point out, though, that negative numbers were very controversial when they were first introduced. And even famous mathematicians like Pascal and so on tried their best to avoid them. They were kind of the sign of the devil or something like that. So it's only through, even in the 18th and 18th century, you had textbooks saying, stay away from negative numbers. They're evil. They don't exist. So
I'll tell you what was controversial. 1/3 of the way into the book, and this is where another aspect of math just comes in, screaming fast, is all the possibilities you create with just a very simple expression. So about 1/3 or halfway through the book, I came across the fact that we'd already written War and Peace, and we'd also created Borges's Library of Babel. Tell us about that.
yeah, so being a writer, I had to put in some literary references. And there are some very interesting things in numbers, just on a very basic level. And that is, supposing you look at a number that starts with a 0, and then put 0.1, 0.12, 0.123, 4, 5, 6, 7, 8, 9, 10. You know, you go on and on like that. You get a nice decimal. 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, what you find in that list is that every single integer, every single whole number will be in that list. Now, as a kid, perhaps you played this game where you said, okay, let A be the number 1, B be the number 2, C be the number 3, and I can code any word that I want and send a secret message to my friend. So for example, the word cab, C-A-B, C was 3, A was 1, B was 2, so it would be the same thing as the number 312, 312. If you look at cab, you know, this number that I constructed, it's in there. It's the 312th entry in that, right? 1, 2, 3, 4, 5, 6, 312 will be there. So the fact that you have written this word, cab, well, that occurs in this number. Now, if you think about it, War and Peace, well, you do a similar code and you write down, I don't know how many, it's like 300,000 words or whatever it is. You write down every single letter in this code, and perhaps you have to do something about punctuation and so on, but you can represent the whole War and Peace by one long integer. You know, it might be in the trillions, but it's the one long integer. If you look at this number, that'll be there somewhere, right? So in the terms of this code, it already exists in this number. Now here's the fascinating thing. If you look at the number pi, it's not been 100% proven, but pretty much proven that every single integer occurs in the number pi. So War and Peace occurs in the number pi as well. So does tomorrow's New York Times. So if you want to look at, you know, what stocks have gone up and so on, just look in the number pi. It's there. There's even been a movie called Pi, which sort of had the same idea. Only problem is that mixed in with War and Peace are similar close by numbers that are utter garbage, you know, in this code. Mixed in with the New York Times from tomorrow are versions where, you know, complete fantasy types of stories are written, so you wouldn't be able to really tell. And this is actually Borges, the Argentinian, I think he was an Argentinian writer, actually has a story that talks about the same idea called the Library of Babel, where there are all these books, and they have all the knowledge in the world, but no one knows where each book is filed. So you can't actually grasp at the knowledge. And this, I think, is a really great metaphor for the information age that we live in. You know, fake news, this, that. We're just bombarded with all this stuff. It's all around us, but you really have to have the key to know what parts are true and what aren't.
So, talking about going into alternate dimensions, which we span many dimensions over the course of your book, we get into hyperbolic space.
And people are probably saying, I knew it. It's going to be all this tough stuff, hyperbolic space. I knew it. Just
right?
wait. Yeah.
But wait, this is where your genius comes in. Metaphor. And you have some brilliant metaphors in this book. And the one I was almost the most taken by was crocheting. Tell us about crocheting in hyperbolic space.
Okay. So this is something, you know, hyperbolic space. What the hell is that? And it turns out that, you know, this isn't my idea. It's actually another mathematician, Dana Tamina, who from Cornell, who came up with this idea. This is something that's a long-standing controversy in mathematics, and that is that, you know, the space we live in is usually called flat space, Euclidean space, and the reason it's called that is because Euclid, you know, several hundred years ago, wrote a book where he wrote down a bunch of assumptions and then derived every theorem that was known in geometry. This book, Euclid's Elements, is the second, it has the most number of editions ever produced in the history of humankind, second only to the Bible. So it's an enormous success, you know. JLF, where, you know, hopefully you can have a spirit come and it'll be a sold-out audience.
You can beam down.
Okay, great. Yeah, so Abraham Lincoln used to carry it in his saddlebag because he said, the way that the thought processes go, he can use that for his legal arguments. So anyway, that's what Euclidean geometry is. One of Euclid's assumptions was always controversial, his so-called fifth axiom. And it turned out that after several centuries, people realized that you could change that assumption. You could tweak it a little, and that you would then get a perfectly different kind of geometry, which was very wonderful, called hyperbolic space, and it actually had manifestations that we can see. But all these forms are quite hard to visualize. And what Dana Tamina, the mathematician, came up with was a way to do it using crochet. So crochet is like knitting, and I didn't know anything about it, so I started looking at crocheting. And I looked at various websites, and there was something very interesting about websites. So in crochet, you might want to crochet a flat circle. And the way you do that is you start in the center and you start going around in circles, and you keep adding knots, much like knitting, and you can keep going round and round and make this circle, flat circle sort of extend, and if you had infinite powers, you could do it all the way to infinity. That would give us our usual Euclidean plane. Now, I don't know if the visual is available, but if so, I would love to get the first visual. Okay, so this is a visual from a crochet website called Spin Cushions. The woman who does it is in Australia, and actually she helped with some of the illustrations. Here you can see that the crochet person has actually been crocheting, but, could we go back to the first? I'm not ready for the second. Okay, so here what's happened is that the person who's crocheting has been a little miserly. They haven't added enough knots, so as you go outwards, the thing is curling inwards, so it's cupping. Now the question is, what would happen if you keep, and I'm still on this one, if you kept increasing, kept kind of being miserly and not giving enough material out, what would happen is that this curl would keep increasing, and eventually you would get a curved surface, and under the right conditions, you would get a sphere. In fact, that's how they tell you to crochet a perfect sphere. So now let's look at the next slide. So in the second slide, what's happened is you've actually added too much material. So when you add too much material, what happens is that this material has to somehow go somewhere. So what it does is it now forms ruffles or ripples along the edges. And if you keep crocheting this, you get something called a hyperbolic space surface. And you're already seeing sort of the prototype example. It's almost like a saddle. It's a saddle shape. And when you keep going, this starts swirling around. Think of lettuce leaves, curly lettuce leaves, or think of certain mushrooms that are curved that way, or nudibranches, like aquatic creatures that have all these ripples in them. So that's what hyperbolic space is. And interestingly enough, you can actually get it through crocheting. If you look at my website, there's a nice picture of a hyperbolic surface. Interestingly enough, mathematicians took a long time to get to this realization, and they were unaware of the mathematical implications of some of these surfaces you see, even though like mushrooms and lettuce seem to know this like thousands of years ago. So they were more knowledgeable about hyperbolic geometry than we are.
Well, bringing that to nature, why does nature want hyperbolic geometry?
So that's a good question. Why would you need hyperbolic geometry? And if you look at a sphere, what's happening is that you have the least surface area. Your surface area is as small as possible for a certain volume. It's a very compact thing. That's what's needed for a seed, for example. If you have a seed, they're often circular. The reason is that you want to actually protect what's inside, the nutrients inside, You don't want too much surface area because the surface is a way for germs to get in, so you want to minimize surface area. On the other hand, sometimes you want to maximize surface area. So for example, for organisms that breathe through their surface, you want to have as much surface area as you can. And that's one of the reasons that organisms will choose a hyperbolic geometry. Some of these are also very good for motion. So once you have these ripples, you can really shoot through the water, as some of these aquatic creatures do.
Yeah, it's amazing actually. I mean, we step through arithmetic and algebra and all of that, and all of that's building up to how nature's using all of that.
Right.
And we talked about how math uses creativity and all the possibilities to express all of this, or nature uses all of those to express itself, and we just teach nature these little, compact forms of expression, and it expands.
Well, that's one of the kind of things in this book, because the traditional way of thinking about mathematics is that we are given nature, and then we as mathematicians or as human beings invent mathematics to explain what nature is. And we never can get it right. We just get it, we can get models that are close enough, but maybe not fully there. In this book, I'm looking at the opposite point of view. I am saying that the mathematician is in the driver's seat, and this is true perfection. The actual state of the universe is this mathematical perfection, and then nature is someone who is trying to actually actualize these formulas or these expressions, but never quite getting it right. And whether you think of nature as God or physics, they're trying to put their own stamp on things. They're saying, no, I'm not going to cede it to mathematicians. I want my imprint on it. And so this is a kind of different way of looking at it. And what it does is it actually gives you some more insight that you don't get the other way. So it's a nice duality.
Yeah, and I think what's interesting about this book is it goes through those, and it sounds like an incredibly arrogant exercise, actually, for us humans. And then you come to this point of humility, which I have always loved Goodell's Incompleteness theorem, and I have to ask you about that. So tell us about how it teaches us humility.
So Goodell was someone who, so before Goodell, there was a mathematician named Hilbert who in around 1900 said that everything in mathematics, we should be able to tell whether the statement is true or false. It's up to mathematicians to bring math up to that level, show that everything is consistent, and you can actually pinpoint each and every statement and answer it mathematically. We might not know the proof right now, but we will find all these proofs. We will know, we must know. In fact, that's what's on his gravestone, some words like that. Well, around, I think it was 1938, 1939, this student wrote a PhD thesis, Goodell, and he showed that if you have a logical system in mathematics in which you can basically do arithmetic, there will always be statements that you cannot prove are either correct or incorrect. So there will always be a statement that you cannot prove, is this true or not? And a very simple example, not exactly what he said, is if you make the statement, this statement is false. Well, is it false? Is it true? If it's false, then the opposite must hold, in which case the statement is true. If the statement is true, the statement is saying this statement is false, well, what does that mean? It's true. Well, that means it's false. So, you get into this logical inconsistency. So Goodell showed that in any mathematical system, you're always going to have these statements which you can't really prove. And this is called undecidability or incompleteness. Now, the fact that with mathematics, which is the most perfect system there is, I mean, if you think about it intellectually, can't think of anything that people have really tightened the screws so much on, gotten everything in order. If with that system you cannot really prove every statement, well, what about other things that aren't that consistent, aren't that perfectly tight? well, you can't expect to prove everything in that too. So, if you're thinking about religion or physics and it can't provide all the answers, well, Gödel's theorem sort of teaches us the humility that, that you were talking about. And I don't think of it as a failing of mathematics. I think it's just a nature of mathematics. And it's not just of mathematics, but it's of knowledge in some sense. That you're never going to be able to really know the answer to everything. There might be an answer, but you might not be able to pinpoint it.
So many more questions, but we're going to pause right now and see about questions from the audience. Ooh, I see hands shooting up.
Wow, 2 hands.
Do we have mics coming up? Yeah.
Hey, so from someone who studied physics in college to someone who left physics and moved to math, I did, in my defense, study groups, rings, fields, and vector spaces, and I'm scarred for life, so good for you. I was also very influenced by a book growing up called Gödel, Escher, Bach.
Yeah,
I mentioned Gödel. If you have not read it, please read it, it's amazing. But some of the things that you talked about, and many times in the earlier example that you were taking about how when you look at a theistic philosophy and you try to subscribe a mathematical solution to that, is math more of a narrative to help explain theism, or because it's pure logic, does it become its own religion?
Okay, that's, let me unpack that question. I think, let me just answer it more generally as what is the relation between math and theism, math and religion. And I think the way that I would look at it is more historically, that math has often been kind of tied in with religion. In the Dark Ages, it was actually the Catholic Church that kept little vestiges of math alive in the West because the monks would do some arithmetic and so on. Later on, we came to figures like Cantor, who talked about infinity. And Cantor was very afraid of being branded heretical like Galileo had by the Catholic Church. And so he actually did things like he sent his work on infinity, because infinity, that's eternal stuff and so on. He sent his work to a cardinal and got his approval, and actually even wrote to the Pope at one point. So I think there are often ways that math and religion interact and theism interacts, but in some sense, math is its own religion. I think that's what comes out of it. So, okay, let's.
Isn't the answer to everything 42?
Yes, of course, yes. In fact, it's on page 42 of my book.
My question over here is, thank you so much. I was wondering if you could speak briefly about over here, hi, numbers which seem to be static, but actually imply movement. And the degree to which I was very impressed, especially during the COVID pandemic, in which modeling began to take place, in which the modeling of numbers would eventually determine where and how the contagion was going to move. And so I wonder if in your book you talk about numbers as a description of movement.
Yes, but particularly that example of COVID. So the first chapter is actually called "The Pope Made Me Write This Book," and you'll have to see what the connection is, but there is a connection. And so with that kind of premise, I was able to put the Pope in throughout the book, so he keeps commenting on the action. And at one point, he is looking over, he gave this sermon the first year of COVID for Easter, and basically there was no one there. And what religion offers, from his point of view, was some sort of strength. We'll get through this. But at the same time, that was one of the periods right after there was a decline in Italy. And so the modeling showed that, yes, we can overcome this. And so that's another form of strength that people can hold on to. And it's extremely important, has been really important. I teach this class, which is math for non-mathematicians. And right in the middle of it, we had COVID, we had to go onto Zoom, and we were just, we were actually making predictions using exponential growth and so on, and the students were just amazed that we made this prediction, and it was exactly right, maybe off by like 5 people or something. So you could really see math in action and how these things work out.
Yeah. I've got a question. The year 2022, if you add your age and the year of your birth, 2022 comes. I tested with every member of the family. The question is, how can you explain the theoretical background of this thing?
If I add my age and what?
But the year of my birth.
Year of
Let's,
what? Okay, if I add
for
my
example,
age.
let's
Yeah.
say I'm 46.
Right, yeah, that makes sense because you just have to write down X plus, whatever your year is, and you will get it right away. So,
So
I'll
my
talk to
question-
you. Yeah, go ahead.
Can you explain the theoretical background, how this happens with 2022?
It's addition.
Well, I cannot
That's
do
all.
it.
That's all I'm going to answer because that's the only answer. It's not a big, deep thing. Just take a piece of paper. You'll see it right away.
But I cannot do in 2023.
You cannot do what?
In 2023.
Yeah, you can. You just have to, your age will be one more, so it'll be exactly the same. So whether you do it 2023, 2024, it'll always be the same. Your birth date plus your age will always give you the year that you're in. So.
I have a question, and this is sort of about numbers and their impact. You talked about your non-mathematician class being impressed with the impact of numbers, and numbers have sort of come to the forefront in a more general way, like if you look at sports analytics and the way people use number theory and math to look at how players perform and figure out how to construct teams. What spaces do you see that kind of number theory coming into play that maybe we haven't seen yet? I would suspect you're on the forefront of seeing these things. Do you have any thoughts that you might want to share or can share with us?
Okay, so I think what you're talking more about is statistics.
Yes.
Like, a lot of these things are played out. I mean, everything these days is based on statistics and pattern recognition and so on. Certainly what you just mentioned about players, their stats, trying to make predictions on where they would work best, like would they be good, in the middle of the game, here or there. All of that can be done by looking at the past and making a compilation of these statistics. This is actually one of the examples used by Cathy O'Neill in an amazing book called Weapons of Math Destruction, where she cites this as an example of algorithms that are actually quite benign. And then she goes on to say how there are so many other ways that this kind of pattern recognition, statistical analysis is pervading our lives, where it is affecting us in very harsh and unpredictable ways. One example that she gives is how, for example, if you're trying to apply for a mortgage, then it is illegal to charge different interest rates depending upon your race. So you're not allowed to do that. So what mortgage lenders do is they've done analysis of this, and they've figured out which zip codes have the highest minority populations. And so they use a proxy, through this analysis and other such things, trying to determine, basically without using the word race, trying to determine these things and then quoting you a different rate based on that. And her book is full of such examples, such insidious examples. So that's, maybe not the most pleasant idea, but we have to get used to this, that pattern recognition is going to be in everything. That's one of the things I really stress in my class. I give them examples from China where, facial recognition is being used in all these things. And it's something that really society will have to, deal with one way or the other.
I think we may have time for just one more question.
Okay. So can you say something about the imaginary numbers and what's the origin of that? And
Yeah, so imaginary numbers, actually there is a section on my book. Remember I was saying you play these games and you don't know how to solve them? Well, supposing I had to start taking square roots and I take the square root of 4, I get 2. I take the square root of 6, I get, whatever, some irrational number. Now, if we are thinking of these numbers as being people or alive, and we are interested in issues of equality, all numbers are created equal. They aren't, but they are. Let's say we have that. Then every number should have a square root too. And when you start looking at a number like -1, well, what is its square root? You can't have +1 because +1 times +1 is +1. You can't have -1 because -1 times -1 is +1. And so mathematicians said, okay, all numbers should have a square root, and that's how they developed the square root of -1, something called an imaginary number. Now, imaginary numbers often, you learn about them if you've taken enough math courses, but you don't really see any use for them. They can't be used for counting. Like, we always think of numbers as being used for counting, 1, 2, 3, 4. So imaginary numbers can't really be used for that. So I had to really think, how am I going to bring imaginary numbers into this narrative? Because I'm trying to construct this narrative as one thing leads to another. And so here's what I did. I said, okay, remember the second thing after the first day, the day 2, is when you create geometry. So I'm going to give each number its own condo unit, I call it. So each number gets a point, and that's how you get a straight line. So, well, all the real numbers, 1, 2, 3, 4, half, this, that, can be accommodated in a real line. But when you come to imaginary numbers, you can't fit them, so you have to find another direction. And that's what gives you not just a line, but a plane. So that's how I deal with imaginary numbers in this narrative.
This is a great place to end it, because imaginary numbers are just a great example of math looking for trouble.
Exactly.
So, yes.
Yes.
So thank you, Manil.
Yeah, and imagine that.
Sorry.
Okay, I'll just finish that thought, because I think imaginary numbers, point to the fact, imagination. I love that connection, that math really talks about, needs imagination as well. So I'll end there. Thank you.
Thank you.
Manil and Maya, thank you. That was totally fascinating, and you captivated my mathematically incompetent brain, so that's really saying something. Thank you so much for coming out here today. We have some gifts we would like to give to you. So the Big Bang of Numbers is on sale at the Brazos book table out in the Grand Hall. I encourage you to purchase a copy, and there will be a signing following that in just a moment. We have all the other books available from our authors that are here from us today as well, and yesterday. We also have the cookbook, Masala from Nita from Pandi. She will be out there as well if you want to have that signed. We will be starting with our next session at 3 o'clock in about 15 minutes. It's called Points of Departure, Nahid Feroz Patel and Sanal Kohli in conversation with Ragini Tharoor Srinivasan. Thank you, and I also want to thank Bella Jane for presenting that talk.
हमारी ओर से सभी को 2022 का